Yeah. All right, welcome everybody. Thank you for joining us for this Geotalk, especially those people in the room. I know it's a busy time of the year with your first drafts due for honors and many people in the field. There's a great audience online, so thank you very much for joining us. For two special guests from China University of Technology, and they're standing behind me. So Professor Chris Volkersdorfer and Elke will go over. Thank you for joining us. And I'm not going to take a lot of time reading this very extensive biography, which is very impressive. You can check that out on the mailer when you got it. But Professor Christian Volkersdorfer is a Saatchi Research Chair in Acid Mine Water Treatment at China University of Technology, the President of the International Mine Waters Association, and a member of the Academy of Sciences in South Africa. And he has 33 years of experience in hydrogeology, mine water geochemistry, and related fields, but has also worked in many other applied geology fields. There's a long list that I won't mention here. He got his PhD in Germany and was habilitated in Germany as well, and has got many projects all over the world and a large research team, and has over, I think, 200 papers. That's a very impressive record. So thank you for joining us. And then his PhD student, Elke, interestingly did a bachelor's degree in geoecology. That might be something that some students in the audience are interested in finding more about, and then went on to do a master's in hydrogeology and engineering geology in Freiburg in Germany. And now she's obviously working in the Saatchi chair for mine water specialization together with Chris. So thank you both for joining us. And there is an incredible range of very interesting things on this table. So hopefully everyone on Zoom can see that. And we'll get started. Over to you, Chris. Thank you.
Okay, thank you very much for your introduction. Thank you very much for being here in the audience. Thank you very much. Here's the camera. Thank you very much for being online with us. For those who are online, I'm sorry you cannot directly participate in the experiments that we prepared for you, because we want to make mine water. I mean, everyone knows that we have mine water around us, but how do we make mine water? That's
Just need to know. Just need to know.
Okay. Perfect. So that's what we are going to do here. So Elke and we brought a couple of things that we want to show you. And we will start with making mine water before we start the presentation. What I brought for you here, and I will pass that around, is where everything starts with our mine water problems. And that is a very beautiful mineral, and that mineral is called pyrite. I will just leave it with pyrite. You know, there are three. That's pyrite, that's marcasite, and pyrrhotite. Always when I say pyrite, I mean the three of them. Yeah? So not just one of them. So the mineralogists here, I'm sorry, I know they are different, but to make it simple, we'll do it like that. And that's from the Wits water strand. So most of you know, when we enter the building, you see it. So that's gold rich. That's very gold rich here. That's where we start. But I also brought you just one pyrite crystal here. Now that's pyrite. I won't let it go around. The last time when I did it, I had to search for it. Someone wanted to take it with her, so not really. So when you expose that to oxygen, what happens? It starts to weather. And when it starts to weather, it means that a lot of chemical reactions that I will show you a little bit later will occur. And after a couple of weeks, months, or years, we have something like that. It disintegrates. Yeah? That's what you can hear here. And one of those disintegrating products that is coming from that weathering is what we call efflorescent salts. And these efflorescent salts, they are storing for us the acid, which then causes low pH values and acidity. And what we are doing now is we will use just normal tap water that I brought from Pretoria. And one of you can measure the pH. So please open it, get in the pH strip, and then we will see what is the pH of the water in Pretoria. And those who are from Pretoria, I know we have two different waters in Pretoria. The hydrogeologist here. This is the mine water. This is the water from where the campus is. That means it comes from the dolomite. Which means we should have a pH of around 7. Can you confirm? pH of around 7. Sorry, online audience, that I'm always away. So we verified that this has a pH of 7 with these pH 6 here. That's what we are expecting. And I know, I hope no one from health and safety is here. I should use gloves now, but let's make it simple. So I have here those efflorescent salts in that container. And what I will simply do is, Elke, could you please talk to that? And I can speak. So what we will simply do is, I will take a little bit of those efflorescent salts, and one of you will just put them into that container. Peter, you said your son has a mind. I think you are qualified. And we're going to take anything first. And then take a little bit of the efflorescent salt. Here maybe the white stuff, which is called those small stuff. That's what we can do. When that happens in nature, then we get something like that. You see here, this is really acidic mine water. I don't call it acid mine drainage, because when I took that sample, it was not acid, but it's acidic. That are two different things. A lot of people don't see the difference. And if you look to the screen here on the left side, and the audience on the video looks to that sample that I have here, that orange sample was taken exactly here. And you see that water here is crystal clear. And then after a couple of weeks, when the iron starts to oxidize, you get that. So what we are working about in our team is on one side, that water that comes out crystal clear, as you can see it here, but then also the water that gets reddish after a while. And that's also a trick. No, it's not a trick, it's tricky. When we're working with mine water, we have to take a lot of parameters immediately in the field. When we take it a couple of weeks later, the water is not the same anymore. And a lot of people don't know that they are sending the cheapest employee that they have into the field to take a water sample. Then it stands for a couple of days somewhere in the lab. Then they analyze that, and the results have nothing to do with the reality anymore. Don't send your cheapest employees into the field. Send those into the field who know what they are doing. Okay, let's see, Peter, what you did. So I have a stirrer here, a small lab stirrer. Let's stir it first. So we're just increasing the chemical reaction speed a little bit here in the stirrer. Okay, that's done. And now I need someone to manage. Okay. So the head of the department, I think head of department is what we call it here, or is that correct? Head of school. Head of school, yeah. Head of school, sorry. She's now going to measure the pH for us, and if I did everything correctly, we should now have acid mine drainage. On 5.5. Okay, so what you could see, so we have a pH of 5 to 5.5 now. It always depends a little bit on how much of the effluent salts goes into that container. So you saw that with those efflorescent salts that come from the pyrite weathering, we make our acidic mine water. I'm saying acidic mine water because it's not acid mine drainage yet. Why is it not acid mine drainage? You will see in a couple of slides. Okay, so let's start with the presentation. So 2 years ago, 3 years ago, just before Corona started, Elke, a colleague of us, and we asked in 3 German mining areas, what do you think, what is mine water? And what you can see on the word cloud behind you is, of course, water, groundwater. That were the words that we heard most often, but we also had toxic. The water will there be forever? It's a problem. It pollutes the environment. We need to pump it. It will cause damage. It will cause guidance. So these are words that we heard from the people, and most of them have negative connotation. So it's not different from what we know. Drainage. Most of the news is bad. We want to bring you the good news because it's much better. Of course, it's our work. Gives us money. How do we see mine water? We see mine water a little bit different. We see it in different colors. We see it as something that we do research. That's a mine water tracer test. This is here in the west front. You see the water is coming out crystal clear after a couple of days, after a couple of meters. It looks like that. This one here is a place that I'm not allowed to speak about, but it's also in South Africa, and it has a pH of 2. So very low pH, a couple of 100 milligrams of liters, couple of 100 milligrams per liter of iron sulfate in the thousands. So that's what you typically would call acid mine drainage. This one here is in Mpumalanga, that is in Sabi. Sabi is one of the only places that I know in South Africa that gets drinking water from mine water. This is mine water. It's coming from a gold mine. So gold mine water does not always mean that it's highly polluted. It can also be drinking water, as here. This one is in Germany. Now, it looks very bad, but the water quality is not that bad. It's directly flowing into a stream where they are fishing. Elke, what is that? Ah, that's in Carolina. No, that's Mpumalanga. It is Carolina. Yeah. So that's where the Council for Geoscience constructed a passive mine water treatment system. So the water here is quite bad, but it comes out again, very nice color. So that's how we see mine water, a wide range of colors, a wide range of chemical composition. So from pH of 2 in that case to a pH of 7.5 in that case. This one also in Germany has a pH of 7.5. So wide range of pH values. We'll come to the pH values a little bit later. Now, what do we consider when we speak about mine water? And some of you might think, in my future career, I will never have to do something with mine water. Why do you know that? We need to know something about the geochemistry. So if you're doing something with geochemistry now, it does not mean that you're not ending up in mine water one day. We need microbiologists, because they help us to understand the chemical reactions that are catalyzed by microorganisms. We need to speak about mine water treatment. That's a book that you see here in front of me. That's the latest book about mine water treatment that I wrote. We need to understand something about the hydrodynamics. So if you are studying physics, for example, if you're interested in physics, these are the people that understand hydrodynamics. Hydrogeologists also understand hydrodynamics, but we need to understand also the effects of the mine water. So effects, we mean when you're a normal person living directly near a mine and you're affected in any way by mine water, these people we also have to address. We also have to speak to them. So this is the broad range of subjects we need to consider in mine water research. Now let's clarify a couple of terms. What is mine water? So you can read much faster than I can speak. So while you're reading it, I can go ahead speaking. We have a definition for mine water. You probably asked yourself, why did I not use a single time? Well, I used it twice, the term AMD or acid mine drainage. That will come shortly. Our team does not use that word because it has a clear definition. And in most cases, we don't have acid mine drainage. So our team uses another word. We will come to that. So mine water is usually used without saying anything about the pH value. It's just a general term for everything. And I wished a lot more people in this country would use just the normal term mine water, instead of saying something that has a clear definition, which is wrong when they use it in many cases. So our team always writes now mining influenced water. This is a word that was introduced in 1997. It's clearly defined what it means. It's nearly every water that somehow was in contact with mining. Mining influenced water. This is the proper word. Here in South Africa, you very often read mining impacted water. That's wrong. It has not been defined, that term. We should make sure that we are using terminology that has clearly been defined. If you want to come up with something new, define it for us so that we know what it is. And now we come to that one, acid mine drainage. And acid mine drainage has also a clear definition. And acid mine drainage is only mine water with a pH below 5.6. So that means the mine water that we made here, now because it's 5.5 to 6, so it could be acid mine drainage, but we don't know it. When mine water has a pH above 5.6, it's not acid mine drainage anymore. So, for example, we have the acid mine drainage water treatment plant in the East Rand. The pH of the water is 6.5, whereas the acid mine drainage. In the whole Witwater Strand, we don't have acid mine drainage anymore. But people speak everywhere that the acid mine drainage is polluting the environment from there. There is no acid mine drainage. And therefore, acid mine drainage cannot pollute the environment. That acid mine drainage, that mine drainage there is acidic, but that's something completely different. Acidity means protons, which is the acid, plus metal acidity. That comes when the metals precipitate, protons are released. And when the protons are released, you're producing acid. And it comes from the humic acids. And if you add all the three together, that water is acidic, but it's not acid mine drainage. Sorry when I'm confusing you here at the beginning and you're hearing that the first time, that important is that we are using correct terminology. And it's not my terminology. That has been defined years ago by specialists that are working with mine water regularly. Kirk Nordstrom, for example, he wrote a very nice paper about that. When the pH is above 8, we speak about alkaline mine water. And when it's between roughly 6 and 8, it's circumneutral. So the mine water in the Witwater Strand, in all the three basins, when it discharges, that's the proper term, when it discharges, not decants. Decant is when I pour that into something, but not when something is freely flowing out. That's a discharge. So when the water discharges, it's circumneutral. So we have circumneutral mine water, which is easy to treat. No, there's absolutely no problem. Okay, that was a little bit about terminology. Now there's someone in the chat, and I heard that I should try to answer in the chat. Yeah. We can answer that later, can't we? That question. But yes, of course, everything that Elke and I or our team is doing is always freely available. We are coming from a group of people that think we are not patenting anything. We are paid by the state and we give it back to the people that pay us. Therefore, no patenting, everything can be freely used. Okay, then you said I need to do that. So how does the mine water evolve? We have an underground mine. So the miners just decided to get bankrupt. The miners decided that all the ore has been taken out from the mine. And then we had just the empty mine. So they stopped pumping them. And Peter just said that his son has to pump a lot of water in his mine in Honduras, did you say? In Honduras. So if he stops running those pumps, that's what we see in the Witwater Strand now, or a couple of years ago, then the water will come up. Then we have a stage where it looks like that. The water that is flowing into the mine is normal groundwater. That's usually not contaminated, only when it gets into contact with those efflorescent salts. Then it becomes acidic, as we added here. Mine is groundwater, which is, in this case, is not contaminated unless it comes from a contaminated stream here. Of course, that's something different. And then at one stage, the mine is completely flooded. That means water flooded the mine completely, and then it's discharging somewhere. Yeah, as we saw it, I think it was in August 2008 in the West Rand. And here, a photograph of how it could look like. Here I climbed down in that mine. Your internet connection is unstable. That's nice. So here I climbed down to the water level in that mine. And that mine was 100 meters deep because the discharge at it was about, I think 1.1 kilometers away from there. And here you can see that bluish crystal clear mine water. pH of that water was 7.5, but we cannot drink it for two reasons. It has elevated arsenic concentrations and asbestos. So we don't want to drink that water. Okay, and if we have an open cast mine, it's the same process, but in that case, we can see how the water is filling up. And then at the end, we have a mining lake. In many, many cases, these lakes really have acid mine drainage. You see that in Mpumalanga, in the open pit mines. And when you look to Google Maps or Google Earth, you see all those red dots there from the acid mine drainage. So a nice red color, as we would see it here. But now let's go to the acid generation process. How do we start to make mine water? That's how we did it manually, but how does Earth do it? How does nature do it? Everything starts with these two really beautiful looking minerals. The upper one here is the marcasite, that's FeS2, so 1 iron, 2 sulfur, and that one is the pyrite. It's exactly the same, 1 iron, 2 sulfur, just 2 different crystal systems. And what happens next is we let that react with water, with oxygen, and someone who helps us in the process, water, oxygen, and then microorganisms. The microorganism that we see here is Aciditheobacillus thiooxidans. And for those of you who are working in mine water, Thiobacillus thiooxidans does not exist anymore. It has been renamed in 2000, but I still read it in publications that people write Thiobacillus thiooxidans. 2000 it has. And the result is that. And I'm showing specifically these two photographs. The upper one is in Germany, 10,000 kilometers away from here. And the lower one is in South Africa, about 200 kilometers away from here. And in both cases, we get the same end product. We get iron. You see here the iron, in that case, here as well. And in that case, it's well buffered. So the pH here is 7, but in that case, the pH is 2. But the processes that lead to there on the right side are exactly the same, no matter where you are on Earth. That's a key thing. So sometimes when I came 10 years ago, I read that the situation in South Africa is special, specific, different. No, it's not different. The chemical processes are the same everywhere in the world. Therefore, it's not different from a chemical point of view. The knowledge is there. The knowledge is there how to treat mine water. And South Africa had the very first zero discharge mine water treatment plant in eMalahleni before others did it. So the knowledge is in the country. But the louder you cry, the more money you get. Know that all of us hate chemical reaction. Every equal sign that you show allows 1/3 of the group to fall asleep. I will show you 5 equal signs. So at the end, you and me, we will be there. The rest will fall asleep. But that's okay. You read the wrong book anyway already. Okay. So, there are more than 4. Even I might fall asleep. Let's start here. That is our pyrite. The pyrite reacts with the water. Now we have 2 different reaction pathways. And that's important for the understanding of the processes. One is the normal oxidation process with water. You always have to add the water, of course. And what we get is the sulfate that is here. And please, ladies and gentlemen, wherever you are, it's sulfate. It's not sulfates. There are no sulfates in the water. It's one sulfate. it's one nitrate, it's one phosphate. Forget the S for the rest of your life. Not when you're a mineralogist. They have sulfates because there are different minerals that can be sulfates. And we get iron 2. Iron 2 is the ferrous iron. The ferrous iron and protons is acid. So you can clearly see that reaction here causes acid and the sulfate, plus that iron that we have. So this is the that's the non-microbiologically activated reaction, and the other one is microorganisms here, and that reacts with the iron 2 and the sulfite, plus the oxygen with the same result here. So here were microorganisms in between involved in that process. And they're really, those microorganisms, because it could be that there's a biologist here. On one side, they're directly feeding on the crystal. They're sitting on the crystal. If you look to a TEM photograph, you can see how they are on the crystal. And others, they don't like that. They're a little bit further away. They wait until sulfate is already sulfate. Now that's easier for them to digest. So they're a little bit further away. But what happens next is a slow and a fast process. We're adding oxygen to that reduced form of iron here. And what happens next is that we get iron 3. It's a ferric iron. And we have another reaction with the pyrite. You see the pyrite was here, but it's here as well. And that also reacts with iron 2. I read that sometimes from some people here in South Africa, oh, we just need to go deep down in the mines. There is no pyrite oxidation anymore. Oxidation happens in 2 ways, the oxygen and the ferrous iron. The ferrous iron also oxidizes the pyrite. It's slower than the oxygen with oxygen, but it's not true that there is no pyrite oxidation anymore in the deeper parts of the mines. It's slow. Yeah. That's true. And what we get at the end is what we call, for example, yellow boy. And in 2 slides, I will show you how it looks like, the iron oxyhydrate. That's the red color that you see here. And you can see, I'll let it go. You see here the sediment at the bottom, that's iron oxide. So now what happens? I told you that that water that is just going around there, when we took the sample, it had a pH of roughly 6.5. So it was circumneutral. If you measure the pH of that one, very likely it will be about 5 or 6. So what happens is exactly what you can see here. Once the iron oxidizes, you're producing, this is the metal acidity, that contributes to the acidity of the water, but not to the acid of the water. The acid only is the protons here. That's what happens. Okay, 2 more for me, and then Elke will take over. Good and bad, that are relative terms. Now we read that we have good wine water, bad wine water. It really depends on what you want to do with the water. It really depends on where you are with your water. So what we read quite often, wine water is bad, it causes pollution with heavy metals. When I read that sentence, my students have to leave the room immediately, because who of you can define what is a heavy metal? No one? That's what I was hoping for. There are 40 different definitions for the term heavy metal. And because we don't know what you mean, we don't use it. And the UPAC is the International Union of Pure and Applied Chemistry. This is the Bible, sorry when I use that word, the Bible for geochemistry, for chemistry. They clearly say we must not use the word heavy metals. So please don't use this. I don't know what you mean with heavy metals. Do you know what a heavy metal star is? I like you because you're sitting in the first. But you know what the heavy metal star is? What is a heavy metal star? It's a musician, of course. But what is it up there? A heavy metal star is a star that has more helium than hydrogen. Because for the astrophysicists, helium is a heavy metal. So if you're writing about the heavy metals in your water, do you mean that you had a lot of helium? It does not. I know that. I'm aware of that. But please, let's use correct terminology. And let's avoid the word heavy metals in the future, because there are simply no heavy metals. If you know what you have, if you have cadmium, if you have lead, if you have mercury or zinc, write it down. Yeah? Do you know how many publications we have in our journals and books that start with heavy metal analysis? The first element is arsenic. Sorry, arsenic is not a metal at all. So how can it be a heavy metal? The next one is aluminum. Are we flying in planes with aluminum? Yes, we are, because it's not heavy. So it's really a confusing word. The key problem is, and that's what we are using, it's the semi-metal and metal contamination of the water. And that causes that our streams, lakes, are contaminated with the ochre that you see here. Yeah? And because the ochre is sitting on the stream bed, the microorganisms cannot feed in the stream bed anymore. And when there are no microorganisms, you don't get other organisms in the water. And then you don't have fish. So it's not the water that is negatively affecting the fish. In most cases, it's they don't have anything to feed because the ochre is there and the microorganisms and zooplankton that cannot start to grow. That's what I just said. So we have a lot of negative effects on all aquatic ecosystems. That means oceans, that means lakes, or that means streams. We see the change in the visual appearance, which you will see in the next slide. And we cannot use it anymore for drinking or irrigation water. But not all mine water is problematic. And with that slide, I hand over to Elke, that is in Wales. We took it last month. You see here a nice stream, and here you see the contaminated water, and Elke wrote it down somewhere, a couple of 100 tons per year of cadmium and lead. And that's a problem for the people there. Okay. And now I hand over to Elke. I don't know how you're going to do that. I thought.
But I'm glad he's done with the chemistry, so I don't have to do that. Let's just quickly check the chat. Okay, we can check this later. Because we talk now about what can be done. Because we're here to find solutions. So let's see what can be done with the mine water. First of all, we need to understand the situation and the problems. So we need to investigate the mine water situation we have. How can this be done? First of all, and most commonly with geochemical, to investigate the geochemical composition. So we take water samples and we analyze them, usually on-site parameters. So we go out there to the mining site and we measure temperature, electrical conductivity, redox potential, oxygen concentration, a handful of parameters. And you measure them in the field because we want to have the direct data from the field and not what the lab analyzes, because then obviously, for example, the temperature is not correct anymore. Then main ions and trace elements, sometimes isotopes and organics. Also sometimes, for example, in Germany, we had a project where we analyzed the mine water for PCBs. So this is one column for the investigation. The second one is to understand the hydrodynamic situation in the mine. And I will talk about all these points in the next slides, a bit more in detail, just for you now to have an overview. So first of all, we can conduct tracer tests. Then we can do depth profile measurements in the flooded mine, even inside a mining lake, but usually inside the flooded shaft. Flow measurement with surface water, but also inside the mine, and analog and numerical modeling. Okay, just an overview. I will come to all of these in the next slides, but there is a third column that we need to look at if we want to understand the mine water situation and the problems that come with it. And this is the longevity of the mine water quality. We call this first flush. Have a look at this curve. You can see there's the mouse. On the y-axis is the total acidity, but this could also be concentration, ion concentration, sulfate concentration. And on the x-axis is the time. And you can see that this point is times 0. And this is when the mine water is first discharging out of the mine. And then usually the concentration or the acidity, the mine water quality gets a bit worse. And then the quality improves over time in a more or less exponential curve. And this process, the change of the mine water quality over time, is called first flush. And it's very important to consider the first flush and the change of the mine water quality, because it really depends how you manage the mine water, because you handle this quality different to this quality. So just keep this in mind. But now let's come to the hydrogeological investigation methods, tracer tests. Tracer tests, as I said, can be done with surface mining influenced water, also inside underground mines. And we use the tracer tests to determine the flow velocity, but also flow paths. So where the water is flowing inside the mine, or for example, also if dams are properly sealed or if mine water is seeping through the dam. Possible tracers are fluorescent dyes, and I brought a few for you here, just for the online people. Beautiful colors, but I can hand them around. It's sodium rhodamine, here's in white, and sodium fluorescein. Then another possible tracer are spores, but they are not really used anymore. And then microspheres. And you can see in this picture here on the top, this is under the UV light. So the microspheres are injected at one side of the mine. And then you measure the concentration at different points in time on another location, and you can count out how many of these microspheres are inside the water. A few pictures for you. This is Prof injecting fluorescent dye, I think the green one, the uranium, inside a mine in Germany, directly into the shaft via a pipe. So it's possible to inject the tracer on the water surface, but we also have a device that we can lower down inside the mine and then inject the tracer at a certain depth. So for example, we have an onsetting station in 200 meters depth, and we want to inject the tracer there. We can open this device and the tracer is injected exactly where we want to have it. Then another application here is an ingress investigation. This is the Blessbox spirit. And we injected also uranium, sodium fluorescein to see how the water ingresses into the mine. And another example, Christian showed it before, this is a settlement pond from a coal mine, and they want the iron to participate. And for this, the water needs to flow as long as possible through the settlement pond. But what happens? The water is taking a shortcut, and you can nicely see this with the green color, that it's not evenly distributed and that it's just flowing there on the side. So we could give the mining company advice to build in barriers to have a more even distribution of the water in the settlement pond. Just a few applications. There are many more for tracer tests, but this is what we mainly use tracers for in mine water research. And if you want to know more about tracers, you can participate on the 12th of September in the webinar, Dye Tracing in Practice. And one of the topics in this webinar with different speakers will be about fluorescent tracer dyes in mining influenced water. Just send us an email, and then I think it's a 2 hours webinar next week. Okay, the next investigation method, it's depth profile measurement. You see one of our colleagues here, he is holding the device. Here a bit more in detail, this is a probe from the company Sea and Sun, and this is the one we have at our lab. And so of course this is the metal device, and the actual probes are on the bottom, and we can measure temperature, electrical conductivity, and the pH value. And just for reference to see how big this device is. So the probe is lower down into the flooded shaft. And then over the depth, we can measure different parameters. And here I have an example for you from a mine in Portugal, Ucharicha mine, a former uranium mine. And we measured temperature and electrical conductivity. You can see this on the x-axis. And the density is calculated from temperature and electrical conductivity with the UNESCO formula. And yes, on the y-axis is the depth of the mine. So what do you see here? What catches your attention? There is a big jump. And the jump is a jump between two water bodies, and we call this stratification. So the mine water body is stratified into an upper water body with a lower temperature and just a electrical conductivity of 800 microsiemens per centimeter. And then we have a lower water body with a higher temperature. I mean, the difference is 4 Kelvin, which is quite a lot, and a very high electrical conductivity. To explain this in greater detail, you need to look at a cross-section. The Santa Barbara shaft is in the middle. This is where we measured. And remember, in 200 meters depth was the jump. And this shows us that there is a warm mineralized layer or water body and a cold fresh water body. And now the interesting thing is that at shaft P4, this is here on the side, the water is discharging from the mine. But the water that is discharging there is only the water from the cold fresh water body. And because of this former uranium mine can treat the mine water just with a relatively small passive treatment plant, and they don't need a big active treatment plant, and because it's just this water of relatively good quality that discharges from the mine. So imagine the stratification would not be there. There would be a much bigger problem. Okay, next investigation method, discharge measurement. You probably all know the impeller method, where you go inside the stream and you measure with an impeller. But there's another method that we preferably use with mining influenced water. And this is the salt dilution method, also called slug injection method. And I would like to explain this to you as well. The S stands for salt bag because we just use normal NaCl, normal table salt. You can see me there in the picture with a big bucket mixing this salt to dilute it with the stream water. So I took a bucket with stream water, put salt inside, and then mixed it. And this is the salt we will inject into the stream, which you can see here. This is also why it's called slug injection, because it needs to be quite fast. And then on the other side, this is here. And with the other side, I mean, this is a certain distance that we choose from the width of the stream. So if the stream is 2 meters wide, we need about 80 to 100 meters of length, just to give you an idea between the injection point and the measuring point. So when we measure, we install usually 2 probes inside the water. And the probes measure the electrical conductivity, but because the electrical conductivity is proportional to the concentration of the salt, we get a nice curve of the concentration. And so there was no tracer injected, and then this tracer cloud that is flowing through the stream is arriving, and we see this nice peak. And then obviously the stream is flushing the tracer out, and the curve goes back down here. And with the area under the curve, we can calculate the discharge of the stream. And this can be done with an Excel spreadsheet and a normal electrical conductivity probe. But our team has a set, it's called TQ Tracer from the company Sommer. And with the software, it shows us directly, while we are still in the field, very accurate data of the discharge of the stream. Last one about hydrogeological investigation methods is modeling. Modeling, you get nice colorful pictures, for example, with free flow or spring, or we also use COMSOL multiphysics. But there's also analog modeling. For example, with the Agricola model mine. This is an analog model that we have at our research chair. And here you can see a picture of the model. So it's the mine with 4 shafts and 4 horizontal levels. And we can conduct very different kind of experiments in this analog mine. So at the moment we are running a tracer test. You can see here tracer and the syringes, and there are sampling ports everywhere in the model. And I take samples after we injected the tracer to see where is the tracer flowing, which flow patterns do we have, how long does it take to flush the tracer out. Why do we do this? Because we prepare a tracer test for a coal mine, and we want to see what is the best setup for such a tracer test. Because in the field you have one chance and it's very expensive, but here we can repeat an experiment every few weeks with different setups, with different tracer concentrations, with different injection points. So it's very nice and it's quite unique. It's the only one in the world. And if you want to come and see it, you can come and visit us at our mine water lab, and we can give you a tour. Okay, back to the actual presentation. What can be done? Because investigation, it doesn't stop there, because we need to have intervention in different phases of the mine life cycle. This can be, for example, in situ remediation. So we can use the stratification and take care, if the stratification exists, not to destroy the stratification, for example, by pumping, or we don't pump at all so that the stratification can develop, because we figured out that in almost every mine worldwide where there is no pumping, stratification develops. So mine water and mine water hydrodynamics need to be understood by the responsible people to make clever decisions to see when can we pump, when can we not pump, should we let stratification develop, because then we have these nice 2 or more water bodies. It's an option. But then what is usually done with mine water, just remove this chat here. Yeah, what is usually done is treatment. And there are 2 main ways for treatment. The first one is active mine water treatment. And this is just now a very short explanation. If you want to read more, I can recommend this book. Active mine water treatment is a physical or chemical process, and human action is required. And usually the pH value is adjusted to reduce the metal solubility, or for acid water, there's neutralization, and then a pH increase for the metal precipitation. The other option to treat mine water, usually mine water that is not so strongly contaminated or polluted, is passive mine water treatment. And this one relies on natural chemical or biological reactions. And there is no addition of chemicals, energy, or both. Okay, just to give you a few examples, because it's always nice to see pictures. This is in Emalachileni, and this is the HDS settling pond. HDS stands for high density sludge. And what you can see here is the process that comes after the neutralization with lime and after the pH increase to participate in the metals. So the sludge is pumped inside here, and then the sludge settles, and then the more or less cleaner water is decanting, and in this case you can say decant, is decanting outside for further treatment. Okay, so this is HDS, and this is one of the most common ones. The next one is reverse osmosis, and this is a type of filtration with extremely small pore sizes. And then freeze crystallization. Freeze crystallization for mine water treatment is very unique for South Africa. It was invented here, and I think this is something South Africans can be proud of, and that we have this very unique treatment method here for mine water. And it uses 1/3 less energy than distillation, for example. And the method is that the pollutants do not incorporate into the ice crystals. So you have the pollutants on the one side and then the ice crystals on the other side. This was active. Now we talk about passive mine water treatment. And I showed you the profiles and the cross-section of this mine in Portugal. And I said at shaft P4, there's a passive mine water treatment plant. And this is this relatively small passive mine water treatment plant. So there are settling points here where the water is flowing out. Then there is a reed bed here. This is also for precipitation. And then there are floating mats here. And this is that the iron reduces, dissipate further. And then the water quality is good enough, and it can just be discharged into the next stream. So passive mine water treatment is very interesting. It's not so common in South Africa, but for example, in the UK, it's widely used. Okay, back to what can be done, because there's a last point that we have to talk about what can be done. And this is monitoring and aftercare. In monitoring and aftercare, we should not forget about this, because, as I said, the mine water changes over time. It's not the same water the year the mine water discharges first from the mine and 10 years later. So water samples need to be taken regularly to check, to monitor how is the quality of the water changing and what needs to be done to improve the situation, or is it fine now, or does it get worse due to any events? And passive mine water treatment is quite nice because you don't need to put in extra energy, but obviously after a while the settlement point is full and then somebody needs to come and excavate the sludge and dispose it. And then also something people not really think about, you put pipes there, but there's incrustation. So after a while also pipes need to be exchanged. Just to give you a few ideas about monitoring and aftercare. Showed the slide of what people think about mine water at the beginning, and almost everybody said, nah, it's bad, it's not good for the environment, it's polluted water. But we should also consider what can be done with mine water, because mine water also has potential. And I would like to show you a few ideas where mine water is used. For example, for drinking and irrigation water after treatment. Here in South Africa, for drinking water, geothermal use of mine water. Usually the water is warm that comes out of the mine, and it can be used for heating of buildings. An example is Springfield in Canada. And the length of the arrows should show you how much is it used to our knowledge worldwide. So you just get an idea where or how mine water is used and in which extent. Sorry. Hydropower. There are past examples, for example, from the Harz or Ore Mountains in Germany, but there are also feasibility studies, for example, in Spain. Then pumped hydropower. Also feasibility studies, but with pumped hydropower, there's always a big risk of earthquakes, just to keep this in mind. Then green energy, micro or mini turbines. This is a picture of a micro or more like a mini turbine. And to our knowledge, and you also talked to other colleagues just when we met them now at the conference in the UK, currently we have no example where micro or mini turbines for green energy productions are used worldwide. Mine water as a resource. Everybody's talking about that we should use mine water for raw earth elements, for lithium, but to our knowledge, this is just in lab stage. Nobody really built a plant until now to really get the resource out of the mine water. Then post-mining use of landscape for open pit mines, but also for underground mines. One of my favorite examples, because a few weeks ago, I was with my kids at Gold Reef City, and these guys told me they use the water they pump out of the mine for the water attraction that is there. So next time when you float around on this ring, just think about that you float on mine water. And health and spa, so they're radon enriched water. Just an example in Bad Gastein in Austria. But we're in South Africa, so we should think what can be done in South Africa, because mine water has potential and we can see the potential. And we can also see the potential in South Africa. And just to give you an idea with the yellow goldish color, this is where we are in South Africa. So geothermal use is not really used, hydropower is not used, green energy not really used. So I want to show you that there is a lot of potential and a lot can be done with mine water. And yes, mine water is not good for the environment, but we need to have new ideas what can be done because it's there, the water. So yeah, just to show you. Second last slide, helpful resources, because I know you're all super interested now in mine water and you want to give up with the normal geology and want to become a mine water expert. So let me show you a few helpful resources. We need to make a bit of advertisement for the International Mine Water Association, because there's the president and I'm the treasurer. So we need to use the chance also for the online people there. So the International Mine Water Association is an NGO. At the moment, we have 500 members worldwide from almost every country you can think of. And they are the mine water experts and they're connected with each other. And we have an annual conference. This year we were in UK, in Wales. Next year we will go to Morgantown in the US, and the year after Portugal, Spain. So it's always everywhere in the world. Also a nice thing to travel. And for you as students, we have a, which is quite, and then you get our own journal, Mine Water and the Environment, 4 times a year. We have a newsletter. We will implement an expert portal now. So let's say I have a question about geothermal application for mine water. I can check in our expert database, and I know I need to call Dave in the UK because he is listed as the expert for this. And we will also implement a young professionals network. Then here in South Africa, there's Visa, Mine Water Division. Then Africa, there's the Mine Water Atlas. Worldwide, especially for acid mine drainage and acid rock drainage, there's a guide. You can check the webpage, or you just can send Prof an email, because he has 32, 33 years now experience and knowledge. So please check the page. A lot of publications are listed that you can download. And as I said, you're all interested now in mine water research, and you will run away from here and come to us. No, joking. We like to go in to the field, but we have the mine water lab. And really, if you want to come and visit our mine water lab, you can come and see it. We have different rooms, and also with the analog model, and check it out. And we also have possible topics for master or PhD thesis. You can see a few here, just ideas, but you can also come with your own idea. And if there are any we can't talk about now, or if you want to participate in the webinar about traces, please send us an email. All right.
Fantastic. Thanks to both of you. That was fascinating, something very different, and I think everyone's really enjoyed it. Right, so time for some questions. Let's first ask the audience here if there are any questions for our two speakers. And if you could come to the front, that would be very useful.
Oh, you mean them?
Yeah, you can come too, but are there any questions in the live audience? For those of you that are online, if you do have a question, all you have to do is raise your hand, and then we'll ask you to unmute. And while we are waiting, there are some questions in the chat. Right, so those are just more comments from Tamiru. Do we have any questions from the audience here? Yes, Jill, would you mind coming to the front?
Yeah.
Thank you very much for a really great presentation. My query is if we have the stratification of mine water and you mentioned in one of your slides that you could pump that for hydrothermal energy. Surely then you're going to be playing around with the transition zone or the change from or the switch from the warm water to the colder water, which is healthier. And then your healthier water is going to drop down. And then it's going to get into the zone where it's going to become warmer and therefore more reactive. And so eventually that's not a long-term solution, is it?
Yeah, so the people that work with geothermal applications for mine water, we connected with them and they said to us, oh yes, stratification, this is also quite new for us. And this is a general thing in the mine water community. People don't know about stratification. They just think it's one big mine water body, which it isn't. So first of all, we need to bring the message out that there is stratification. And we are discussing with them that it might be an option to have a closed system so that you don't actually pump the mine water. It's just you send a liquid in a closed pipe through the warm mine water so that you have less mixing. Or the other idea is that you that extraction and infiltration well needs to be very far away from each other. But we personally have no experience yet with it, just ideas that are floating around. And yes, it's important to consider the stratification.
Thank you.
Yes.
Yeah, so what Elke said about the closed system, that's like a freezer or you put it on it, but it's the way around, of course. No? So the liquid, the organic liquid gets heated. In the deeper parts of the mine, it's coming up again, and then you can use it for heating. It's cooled down, and then it goes back. There's only one application so far in the world in Germany where they are using that application. All the other alternative would be use the water that is flowing out of them. Because then you don't have to. That's also done. That's also done there. Worldwide, there are roughly 100 applications at them.
Yeah, and of course, if you use the water that's flowing out, then you're not distracting the system.
But even if you use the water flowing out, presumably then your stratification is going to go this way. Does it not do that?
No, it doesn't. The stratification stays stable. I mean, the longest record we have is 35 years. So it doesn't.
Right. Do we have any other questions from the audience? Yes.
A question, a certain idea. Out of East Rand, there are people mining the reed beds from the sands. It accumulated, those reeds accumulated gold over many years. And they mined it about this thick black sludge with reed roots in it, sent it to Ergo, and got very good recoveries. So as a nice project for one of your students, find a good reed that likes gold catching, and pick how much gold is in the mine. Maybe you've got a business. And you don't have to sell books, you can mine gold.
It's a very good idea. A friend of mine, she just bought a small gold mine in Finland. I will plant a reed bed there.
Right, we have one question from Nontlanta online. It says, how do you dispose of the sludge?
Yeah, most people are disposing them off at waste disposal sites. That is the normal way of doing it. But the preferred way is how it was done when the first high-density sludge mine water treatment plant was constructed in the world in 1973 in the US. They discharged the sludge back into the mine workings. And that's what we are doing in the East Rand here. So the East Rand mine water treatment plant is discharging the sludge back into the mine workings. And when it's far away from the main shaft, then you don't get the sludge back into the water stream. The advantage is also that the sludge still contains a little bit of alkalinity, which also means that you are increasing the pH. That's also an advantage. Sometimes I hear people saying, oh yeah, but what happens when the metals dissolve again? But these people should read a little bit more about chemistry. When you have the metal there, and around the metal you have the sludge with a high pH value, it's like isolating that metal, so it does not dissolve. I did experiments there for a German mine many years ago. A Canadian colleague did do a lot of experiments at a Canadian mine where they are also discharging the sludge back underground. We don't have a single case where we saw that the sludge negatively affected the water when it was pumped back into the underground. When it's far away from the central shaft where you're pumping, far away means minimum we notice is 500 to 600 meters. That's far away.
Okay, Suman, would you mind coming to the microphone, because otherwise
Yeah,
audience
the
online won't
audience,
see you.
online won't see much.
Is it possible to recrystallize the mine water by decreasing the pH? And also, what is the effect of pressure and temperature on the mine waters?
So what was your first part of the question?
If we decrease the pH, can you recrystallize the mine water?
Recrystallize, can you precipitate?
Yeah.
Metals.
In the mine.
In the mine water, yeah.
Yeah.
Okay.
That is what is done when you're increasing the pH, and the iron will precipitate.
Yeah, can remind that, like, we can, after decreasing the pH, you can remind that if you like.
Or say, did you say decrease, going down?
Yeah. Like,
No, when the pH goes down, you're dissolving everything again.
I'm increasing, sorry, increasing.
I
the
mean
pH.
increasing.
Yeah.
Yeah, that is done. That's a normal, what Elke said, mine water treatment process, increasing the pH, and then the metals precipitate.
And presumably that's where you could harvest things like critical metals from that, right?
Yeah, you
If it-
could do
if
that,
you
but
pres-
that's what Elke pointed out. We have about 20 years research. No one did it so far. It's only at the lab stage.
Okay.
And a colleague of mine, he nicely says, you're spending a lot of money in getting out a little bit of iron, or a little bit of the rare earth elements. If I look into my mine, I have a caterpillar like that gives me 2 tons an hour, and it costs me more or less nothing. And you want to spend that much money in getting out that tiny little bit from the mine water. So we are not there yet.
Okay.
It's like the needle in the haystack.
Also, what is the effect of pressure and temperature in mine water? Like, is there any research?
On what, sorry?
Pressure and temperature.
Sorry, what?
Pressure and temperature.
Oh yeah, that's what we are doing in our research team.
Okay.
Yeah, that's what is done. Yeah.
All right.
Yeah. Thank you.
Okay, do we have any more questions from the room? Nothing online. So just once again, thank you both very much for coming. It's been a great pleasure to have you here. And hopefully we can visit your institute.
Yeah,
Come
absolutely.
Yes, please.
and visit.
Absolutely, yeah.
All right, thanks everyone. We'll see you next week. Juggermore, getting a question.
Yeah, thank you as well.
Okay,
Yeah,
thanks everyone.
Thank you for listening to us. I'll see you soon next week.
Great.